of my presentation is about the data quality issues in the geographic information system. As a partial result from my research, the stochastic simulation model of point and line segment will be introduced. And these stochastic simulation models will be compared to the corresponding analytical error models in the internal validation, and conclusion and future study will be made in the last part. Increasing needs of spatial information for various areas, GIS has been recognized as a practical tool for spatial problem solving and decision making. However, fundamental concerns arise from the fact that GIS involves the spatial data from multiple sources and different types, and positional uncertainties exist in spatial data, as shown in the pictures on the slide. Also, experienced GIS users have come to realize that different application requires spatial data at different accuracies. Also, dubious spatial data creates problems rather than satisfying their needs. To deal with the problems concerning the data qualities, error models in GIS are used to characterize positional errors in spatial data, also propagate the errors through the spatial processes. Generally, there are two distinctive approaches for modeling positional errors, analytical and simulation. The analytical error models is derived by applying the law of error propagation to the covariance matrix and visually describe the positional error distribution along the spatial data. Simulation error model indicates the positional error distribution by generating error-corrupted versions of the same spatial data. However, due to the different approaches for modeling positional errors, it is necessary to make certain whether those error models predict correct errors in the given set of conditions. Therefore, this presentation introduced the stochastic error models and to be compared with the analytical error models for point and line segment. Error ellipse is the typical error models for the point measurement. Like the pictures on the slide, these error ellipse has different shapes, size, and orientation depending on the parameters in the covariance matrix. Not many, but few analytical error models for line segment have been proposed in the GIS community. Epsilon error band is the one of the most common error model for the line data. This is widely used for error description and uncertainty assessment and error handling function and generalization in the geographic information system. This model is developed with a constant distance from the either side of the line segment. However, this model doesn't have a rigorous statistical basis to describe the positional errors. Later, error band model was developed with the statistics and probability theory. Positional error distribution by this error model is represented with bivariate normal distribution at the end of 2 points, when the set of normal distribution perpendicular to the line segment. Eventually, this error band model has a minimum width in the middle and maximum width at the two end points. The error band model in the previous slide was further developed to describe the spatial correlation in and between XY components of the two end points of the line segment. In this model, any point along the line segment is determined by the linear function as below, error ellipses of the points are derived by the law of error function to the linear function. This error band model can then be constructed by aggregating all of those error ellipses. This slide shows the stochastic simulation model to be compared with the error ellipse. In this stochastic simulation model, and Box-Muller method and rotation matrix is used to populate the positional errors in the point data. Box-Muller method generates the pairs of random numbers from the normal distribution with zero mean and univariance. Because the principal axis of the positional error distribution is coincides with the semi-major axis and semi-minor axis of the error ellipse, the standard deviation from the covariance matrix needs to be transformed using these equations. These transformed standard deviation is used as scale factors, random numbers from the Box-Muller method. The generated random errors need to be transformed back to the XY space using this rotation matrix will be added to the original point coordinates for the perturbation. In this slide, stochastic simulation model based on Cholesky decomposition is shown to generate error-corrected versions of the line segment. In this slide, input parameters came from covariance matrix for the line segment. And the correlation matrix is factorized by the Cholesky decompositions, and matrix for the random pairs is also generated by the Box-Muller method. And correlated random numbers can be generated by the multiplying the matrix B with the random error matrix. Also, standard deviation is used as a scale factor to the correlated random numbers. In every repetition, the generated random numbers will be added to the corresponding components of the two endpoints of the line segment. Internal validation is designed to test whether those error models predict correct positional error given set of conditions, for which theoretical description by the analytical error model will be compared to set of positional errors by the stochastic simulation model. The stochastic simulation model will be validated when the difference between two error distributions fall within predetermined tolerance. This slide shows the validation process for the point error model. In the validation process, simulation result will be compared to the error ellipses with the different confidence regions. In actual simulation, 10,000 points are perturbed with the equal variance and unequal variance. This picture shows the example of the point model validation. In this slide, 100 points are perturbed by the stochastic simulation model. Also, corresponding error ellipse has the confidence region of 39.4%. Simulation result indicates that 40 out of 100 points fall within this error ellipse. The difference between the number of GPS data points that fall within error ellipse is almost identical to the confidence region. Next three slides shows the simulation result with an equal variance and unequal variance. X-axis shows the correlation varying from -1 to 1. Each interval is 0.1. And y-axis is the average percentage of the points that fell within corresponding confidence region. Although all of those graphs fluctuate in random patterns, the difference between average percentage and corresponding confidence regions are within 0.5%. This simulation result indicates that the stochastic simulation model realized the intended nature of positional errors in the point data. This slide shows the validation process for the line segment. In this process, group of 300 simulation results will be compared different types of error band models with 99% confidence region. In this slide, simulation results are compared with the epsilon band model and error band model. In this slide, X1 indicates the X component of the left endpoint, and X2 indicates the X component of the right endpoint. And Y1, Y2 can be interpreted in the same way. The covariance matrix for the epsilon error band indicates that X and Y components of the two endpoints has the equal variance. However, correlation matrix indicates that X and Y components of the left endpoints has the positive correlation with the corresponding components of the right endpoint. Therefore, in the simulation, all the simulated line segments are parallel to the original line segment. They are perturbed with an equal direction and equal magnitude of displacement from the original line segment. Also, in the normal distribution-based simulation, line segment close to the original line segment has a higher frequency than other line segments. Also, a set of simulated line segments has an equal distance from the either side of the original line segment. Error band model shows that two endpoints are independent of each other. Also, they have equal variance. Like the error description by the error band model, the simulation result has a minimum width in the middle and maximum width at the two endpoints. In this slide, the simulation results are compared with the two different types of error band model. In the correlation matrix, covariance matrix indicates that, like the error band model in the previous slide, two endpoints are independent of each other. However, right, left endpoint has the positive correlation, and left components of the XY components of the right endpoints have the negative correlation. Therefore, in the simulation, the set of simulated line segments have the minimum width. However, simulation results at the two endpoints are skewed with the opposite direction. In the third error band model, XY components has the bigger variance than those in the right endpoints. So, simulation result is dispersed wider than those in the right endpoint. Also, Y components of the left endpoint has the negative correlation to the XY components of the right endpoint. This negative correlation tends to perturb the right endpoints the opposite direction with respect to the original line segment comparing to the left endpoint. Okay, research indicates that its stochastic simulation model realizes the positional uncertainties of same spatial data. Simulation and analytical error model is suitable for simulating and describing positional errors. Due to the simplicity of implementation, the stochastic simulation model for line segment is easily extended to the string. However, this research only concerned about the positional error distribution in spatial data, so it is necessary to implement those stochastic simulation model into the GIS also to investigate the error propagation, its effect on the output product from the GIS-based application. Thank you.
Thank you for your presentation. Questions or comments? I have a question. What's the main advantage of your approach compared to other models?
Could you say that again?
What's your main advantage of your approach?
It's very straightforward comparing to other stochastic simulation model. Are you talking about some approach to validate those two kinds of model, or talking about only about the stochastic simulation?
Your simulation model.
Yeah. Okay.
Compared to other error models.
Okay. I think this is critically important about the stochastic simulation model. I don't believe that there is generic error model for all types of spatial data and data source. This stochastic simulation model is useful for the hard-edged spatial feature with explicit corner. After making the surveying technique to the corner of the spatial measurement, you can derive the covariance matrix after adjustment. So after implementing those stochastic simulation model in the GIS, you can estimate the degree of uncertainty like polygon area and perimeter. Yeah. I think this is one of the advantages of this stochastic simulation model.
Yes, thank you. Any other questions or comments? Please.
Thank you for your presentation, Bruce. I think it is very nice, but my question is very simple. I heard this presentation, which is kind of very complicated to me, but what I just want to know is what's the practical example that you can apply this, your research on the real case. Could you show me some examples?
As I said at the beginning of this presentation, this error model is defined the positional error distribution in the spatial data like point and line and polygon, and used to propagate those positional uncertainties into the output product through the spatial operation. This error model is used to describe the error distribution along the all types of the spatial data used in the GIS. This can be used for the build standard required for certain types of GIS-based applications. Also, in terms of the estimate uncertainties in the output product, this error model used to estimate degree of uncertainties in the areas. So suppose that you have a landing information system, and you can apply the various types of surveying technique. For example, like a ruler to measure from the 100 meter away from the control point, the uncertainties in the aerial measurement is become very larger. So areas of the polygon impact on the cost of land purchase. So in case of the urban area, if you measure the area with the surveying technique, you have to apply surveying technique with a higher accuracy. However, in the rural area, you can apply cheap surveying technique. because uncertainties in the area measurement is not sensitive to the property owner. Does it make sense to your question?
Yeah, I guess we still have time for short question. Any questions? No? Let's send the presenter again.